So, thank you Raghavan for the nice kind introduction. So, we are going to look at some things in multivariate calculus, that is a topic assigned to me here. So, whatever we do in analysis, we are always taking limits. So, that is our job most of the time. Every process we define continuity, differentiability, integrability, etc. Everything is a limit of some kind or the other which we have to take. When we are in real line, it is not too difficult, because you can either, when you want x going to a, you can either go from below or you can go from above. So, there is only one direction you have to worry about. Of course, you can jump both ways, but still there is essentially one direction in which we are moving. But once we go to many variables, then the situation is complicated, because there are many ways of approaching a point, not just along this. So, the notion of a limit has to be understood fairly carefully, and so what do we mean by saying, so f is, say, from R2, let us say, to R, you can think of Rn in general. So, what do we mean by saying limit of f of x as x tends to a? So, x now is a vector, it is a 2 x1 x2, a is a1 a2 and so on. So, when we say that this is equal to L, for the moment let us assume that it is finite. What do we mean? We mean by saying that given any epsilon positive, there exists a delta positive such that norm x minus a less than delta implies norm mod fx minus fa is less than epsilon. So, what is this expression here? So, norm x square is sigma mod xi square. So, norm of x minus a is the usual distance, as you know, sigma mod xi minus ai whole square. So, we have a point here. So, for all points in this ball, fx minus fa should be less than epsilon. So, now let me define. So, we have this is the first notion of a limit. Now, since we are in R2, then we have some natural ways we can think of limits. So, we can think of, say, iterated limits. So, f of x y, I can take limit y tending to b, limit x tending to a. So, I may try to do this in two ways, two steps. Okay. Then I can also think of limit x tending to a of f x y, limit y tending to b. I try to do it in this way also. So, the question immediately arises, are these the same? So, first of all, we have the following proposition. So, if limit x tending to a f of x equal to L, then the same limit is achieved along any path. What do I mean by this? So, what is a path? A path is a continuous function from, say, 0 1 into R2. So, when I say I am approaching this limit, suppose phi of t naught equal to a, then what do I mean by saying the limit along this path. So, I take f of phi of t limit t tending to t naught. This is what I mean by saying the limit along that path. So, I have a point here, I move along like this. So, this is the function phi of t, this is the path. So, I evaluate the function phi of t on this, and now it becomes a function of one variable, and I am taking the limit as t goes to t naught. Now, so this I am claiming should also be the same as the original limit. Why? Because when t there exists eta such that mod t minus t naught less than eta implies phi of t belongs to the ball center A, radius delta. Phi t is a continuous function, and therefore, its distance from phi of t naught should be small whenever t minus t naught is small. So, after some time phi of t will sit inside this, but then you already know that f of x minus f of a is less than epsilon. So, f of phi of t minus f of phi of t naught will be less than epsilon whenever t minus t naught is less than eta. So, we achieve the same limit along any path. So, how do you use this theorem? The way of using this theorem is to show that suppose I have two paths along which I get different limits, then I will say the limit does not exist. Because if the limit exists, then it should be the same along any path. So, the way of, but there are millions of paths, so you cannot check it on every path, but you can use it as a negative test. Namely, if the limit does not exist along, or it is different along two different paths, then the whole limit cannot exist. So, that is the way. So, corollary, if the limit is different along different paths, then limit f of x as x goes to a does not exist. So, that is the conclusion you can do. So, any path should give you the same limit. So, if I have different paths. Okay. So, we will see an example in a few moments. Before that, let me polish off one more result, so proposition. So, let me call, we have three kinds of limits here. So, first is this limit f of x as x tends to a, which I have defined here. This is the second and this is the third. Okay. So, if one exists, that means the limit as x tends to a f of x exists, and if 2 or 3 exist, then the limits are equal. So, if 1 and 2 exist, then the limit has to be the same. If 1 and 3 exist, the limit has to be the same. But mind you, I am not saying very much. I am just saying if every time. Okay. So, we will see examples now where what will happen. Okay. So, let us say 1 and 2 exist. So, the proof of the other thing will be very similar. So, you have that mod f x minus f of a is less than epsilon for all norm x minus a less than delta. This we know. So, you now fix what? Fix x. Fix x such that norm x minus a, okay, no, let us fix x. such that, okay, let me just still do that, mod x1 minus a1 is less than that. This is A. So, I am taking x somewhere in this area, in this range. Then as, so you now define g of x, g of say y equals f of x y. Then as y tends to b, x y will belong to this ball. So, let us call this ball this ball. So, as y approaches b, x y has to belong to this ball, because I am fixing an x somewhere here. So, I am moving along this line, this is x fixed. Okay. As y approaches b, either from this side or from this side, after some time it has to be inside this ball. Okay. This implies mod gx minus f of a, which is L, is less than epsilon. So, this is not, because the limit is L, it is not f of a, I am not talking of a continuous function, sorry. Okay. So, gx minus L has to be less than epsilon, and this is true for all y such that it is close to x, this, and therefore, limit of gx as x tends to a is equal to L, because this is true always. Okay. So, that means limit of y tending to b, x tending to a f of x y is the same as. Similarly, if you had this limit exists, you proceed like this. You will first come like this, and then you will come like this. So, once after some time you are always inside this ball, the distance from L should be less than epsilon, and therefore. So, we made a lot of statements about if this limit exists, this is the same, if that limit exists, the same, and so on and so forth. So, let us see some examples and see what is the exact situation. So, examples. So, let me define f of x y equals x y by x square plus y square if x y is not 0 0 and 0 if x y is 0. Then let me look at the path y equals mx. This is a straight line passing through the origin with slope m. So, if I put y equals mx and let x tend to 0, okay, then what do I get here? I get mx square by x square by m square x square, which is m by 1 plus m square. So, what is the limit as x tends to 0 along any of these paths? the limit is m by 1 plus m square, and that changes for each m. So, if you change the straight line, the limit is going to be the same. Therefore, 1 does not exist. Because on different paths we are getting different limits, but we said that if the limit exists 1, it should be the same on every path. So, now I have produced paths for you which are different, and therefore, the limit does not exist. But what about 2 and 3? So, you first allow y to go to 0, then this will become 0, and then you let x go to 0, so you will get 0. Similarly, if you let x go to 0 keeping y fixed and then let x, okay, you will again get 0. So, 1 does not exist, but 2 and 3 exist. So, now let us look at f of x y equals x plus y sine 1 by x if x is not 0 and 0. So, so you want limit x y tending to 0 0 of f of x y. Does this exist or not? But what is mod of f of x y? Is less than or equal to mod x plus mod y. Modulus of sine is less than or equal to 1. So, I can say. So, if x y goes to 0, this can be made as small as you like, and therefore, this is equal to 0. So, 1 exists. Three also exists, or rather 2 exists. You let y go to 0, keep x fixed, this term disappears, now x goes to 0, so you get 0. So, 2 limit is 0, and you see 1 existed, you got 0, 2 existed, you will have to get 0, you cannot get any other thing by the previous theorem which we said. But 3 does not exist, because if you fix y and let x go to 0, sin 1 by x does not have a limit. So, there is no limit, and therefore, 3 does not exist. So, now you can immediately interchange the roles of x and y in this example. So, you will get 1 exists and is equal to 0, 3 exists, but 2 does not exist. Yeah. Yeah. Yeah.
And we multiply it with the y.
Mm.
And when we apply, so when we first apply that fluctuating function, so we'll be getting x plus y into an epsilon. That epsilon will for the minus 1 and 1.
Yeah.
Now I let y to go to 0 and epsilon.
Yeah, if y goes to 0, limit does not exist. That is what I have told you. No, whatever x y you take in the neighborhood of the origin, f of x y is less than mod x plus mod y. Do you agree or not? Yeah. So, that is enough. So, f of x y minus f y minus 0 is less than epsilon, right. Yeah.
If 1 exists,
Yeah.
that is the
Ah.
That doesn't guarantee 2 and 3 exist. That's what
No, that's
that's this example.
that's the example. Okay. Nothing guarantees anything else. That is the whole moral of the story. All these examples we say 1, 2, 3 are 3 different people. Their behavior are not controlled by anybody else. I mean, they don't control the behavior of each other. Okay. But if one exists and one of the other two exists,
Go back to the basic fundamental limit.
yeah,
Limit x tending to a comma b f of x is for every epsilon greater than 0, there exists a delta greater than 0, such that the norm of x minus a comma b is less than delta, implies that modulus of f of x minus that value n is less than epsilon.
correct.
That is the definition which one points to.
Yeah.
If that is the definition which one points to, that is the definition of the limit itself. And when we say one is existing, how can we say that 2 and 3 may not exist?
Yeah, because 2 and 3 are given by some other methods. You see, when I do 2 and 3, I fix an x and I go like, see, always in analysis when you have different two limit processes, you have to be very careful whether you can do it in any order or whether you can do it at all and so on. Like take differentiation under the integration sign. It may not always be true that you can take the derivative inside. Okay. If a function fn converges to f, then integral fn may not converge to integral f, because you are having two juxtaposing two limit processes, and here the same thing we are doing. We are first taking a limit as y tends to b and then taking a limit as x tends to a. That is not taking, I am not taking the limit on this path, you must be clear about that. If I did that, then of course it is the same as the first one. But what I am doing is I am first coming like this and stopping each time and then taking all these limits. See, for a fixed x taking y tending to b means for every x I take a limit like this and then I take the limit of all those limits. Now that is different from going like this, maybe that is your confusion, okay. And I am saying they are different, okay. So now third example, you take f of x y equals x sine 1 by y plus y sine 1 by x. Then again mod of f x y is less than or equal to mod x plus mod y. So, the limit 1 exists, but neither 2 nor 3 exist. So, you cannot say take for granted anything. The only thing you can take for granted is if 1 exists, then you can come to a b along any path you like, that is one thing. Secondly, if 1 exists and one of the other things exists, they will not be different, okay. That is good news. But the bad news is that you can't do what you like. I mean, you can't say this is easy for me, let me first take one limit and then take the other limit. No, that you cannot expect it to be the same as the original limit, okay.
Maybe she was asking because the first one is the definition.
Yeah, yeah.
So, after getting first one is exists, we may not need to check 2 and 3.
Yeah, these are all questions. When you see the first one is difficult to compute, okay. Sometimes I can get away with some simple estimates just to do an example on the blackboard, I will do something. But given if I give you a function, it may be difficult to get that. You may be able to prove that limit exists, but you may not be able to compute it directly, okay. Very often this happens, you know some function can be integrated, but you tell me give me the integral, you will not be able to, okay. So, like that. So, if you know the limit exists, but you do not know, okay, then these are 2 and 3 are aids to computation. They reduce your problem to simpler problems and you try to solve it. Now, the question is, can you trust that answer or not? So, this theorem tells you when you can trust, when you cannot trust, okay. 2 and 3 are not part of a definition, they are just iterated limits. It is like double integral. I tell you double integral exists or double summation if you have series. Now, what is your first tendency? I will sum with respect to one variable, then I will sum with respect to the other. Now, the answer is, the sad news is that it may not be the correct answer. Okay? Yeah.
When x takes the value 0, y takes any value, what is the nature of the function?
Yeah, it is that, I mean, it's that function, that's it.
Maybe the function may not be well defined when x is 0. And
Oh, okay. So, okay, I think I wrote it wrongly. If x is not 0, and if x is okay. So, yeah, good that I may make mistakes on the blackboard. So, good to be correct. Fine. Yeah. So, if that was your confusion, then of course I am sorry. Yeah. Okay. So, now we know where we stand, where all these limits go. So, now is the question of derivative. So, you all know suppose f is from R to R. So, if I want to study the derivative at a point A, then you look at the limit as h goes to 0, f of a plus h minus f of a divided by h, and you will say if it exists, this is what you call the derivative of f. Now, we would like to extend this definition to higher dimensions. One way is you doing the one which you probably teach regularly is the partial derivative. So, you go, but that is what are you doing? You are moving along one direction. So, that is really cheating. So, you are just moving along some particular preferred directions, but we would like to know if you can extend the notion of a derivative without resorting to a particular direction or particular path. So, how do we define it? Now, obviously it has to do something with this difference, f of a plus h by f of a. Now, I cannot divide by h because now h is a vector, a is a vector, so h is also a vector. So, I cannot write this definition. There is one more equivalent definition which says that f of a plus h minus f of a minus f dash a of h. So, I am just multiplying out and bringing everything to one side. This has to go to 0 as h goes to 0. Okay. So, equal to epsilon h, where epsilon h by h goes to 0 as h goes to 0. This is equivalent definition for the derivative. This is the starting point of the Taylor expansion. This is where you start from. So, you write f of a plus h minus f of a and linearize it, okay, replace it by a straight line, okay, tangent, and then there is a small error which you make, and how small must that error be? It is not enough if it just goes to 0, but as you divide by h, it must go to 0. So, this is a stronger requirement than just going to 0. It is not enough to be a small error, it must be a very small error. Okay. So, this notation I will give you when I say little o of mod h, this means this some function epsilon of h which obeys this rule. Okay. This is a convenient way we write in analysis instead of writing every time so many functions and so on. So, we will say this is of the small order. When you say big O, that means it is bounded by a constant times that quantity. When I say small o, that means when I divide and then go to 0, even then the limit has to go to 0. So, we will say f of a plus h minus f of a minus f dash a of h is little o of mod h. That means exactly this, whatever I have written. Okay. Little o means this notation. So, just understand this notation, it is nothing it is just a notation, nothing more. When I say this, I mean that it is equal to a function epsilon h such that epsilon h by h goes to 0 as h goes to 0. Okay. So, this is how do we use this now? Okay. Now, at this point I have to ask a question. How many of you are familiar with nonlinear spaces? How many of you have heard of this? Heard. Some functional analysis you have done? You have MSc student, you have all done MSc, no? Okay. Because at no extra cost I can do some things. If I use that language, it is more convenient. But if you are uncomfortable, you can always, I will tell you what you should think. Okay. So, let me give you a small crash course in 10 minutes about what I will use, and if still you are not comfortable, I will tell you what you should do when I talk. Okay. So, what is functional analysis? It is just a marriage of analysis and algebra. Okay. So, you have linear algebra, you have okay, and then so you have V is a vector space, and on that you define a norm. So, norm is like distance, okay, or the norm of a vector, modulus of a vector, and so on. So, you have norm x is always greater than or equal to 0 and equal to 0 if and only if x equal to 0. Norm of any alpha x, where alpha is a constant in the scalar field, this is mod alpha times norm x. And the third is the most important, called the triangle inequality, which is norm x plus norm y. So, anything with these three properties is called a norm. So, examples, so you take R2 or Rn. So, norm of x is equal to sigma mod xi square. It has all these properties. How do you get the third one? This just says two sides of a triangle is bigger than the third side. It is just the analytic version of that geometric theorem which you learn in high school. So, that is why it is called the triangle inequality. Okay. So, another norm you can do. So, I will call this norm 2, I will call this norm 1, this is sigma mod xi. This is also a norm, you can verify all these properties. And there is one more. But you can do for Rn, whatever I have done here, you can generalize to R. Vector space over reals or complex numbers, it does not matter. Okay. So, vector space over R or C. But we will, throughout this course lectures, we will talk of real. Okay. So, what does the first one mean? So, if you take norm of x minus y, this obeys all the properties of a distance of a metric. So, you get a metric space immediately. So, the first one says, if I have 2 points, is the distance what we call as the crow flies. The second one, suppose you are living in a city like New York, where you have roads which are one direction, they are all called avenues, on the direction they are all called streets. You can't fly from one place to another. So, you have to travel along the road to reach another place. So, when I want to say this place is so much distance from the other place, the realistic thing is not as the crow flies, but how much I have to walk. Okay. and that is given by this one. And the third one says in each direction what is the maximum distance I travel. Okay, so these are examples, there are many more, okay, there are several. The thing is they all give you the same topology, okay, namely the open sets are the same, the etc. etc. If you look at the unit ball in norm 2, then you know it is really a ball. If you look at this norm, so that is mod x plus mod y equal to 1. So the line will be these 4 lines. So this will be the unit ball in, if you look at this norm. So a vector space with this gives you a metric space, so I can talk of convergence, everything. Okay. Metric space all of you know. Okay. So I can talk of convergence when a vector converges to another vector, that means when norm, so xn converges to x means there exists a capital N such that for all n bigger than or equal to capital N, norm of xn minus x is less than epsilon. So this is what we mean by saying convergence. So once you have convergence, you can talk of continuity and all these things. So, but we are not interested in continuity of everything. Well, we are to some extent, we are even going to talk of differentiability. But first of all, the easiest thing we want to talk of is continuous linear transformations. So, T from, so E, F are normed linear spaces. That means E is a vector space with some norm, F is another vector space with another norm, and you look at E to F, a linear transformation. So what is linear transformation? T of alpha x plus beta y is alpha Tx plus beta Ty. So this is called a linear transformation. So if T is also continuous, then you call it a continuous linear transformation. Okay. Good news is, if you take Rn to Rm, any linear map is continuous, so you don't have to worry. Okay. This is only if you are looking at infinite dimensional spaces. Okay. So if you are not interested in that, forget about what, think of this. Okay. Now you have the following equivalent properties. T is continuous. That means continuous at every point. 2, T is continuous at the origin. 3, T maps bounded sets to bounded sets. All these 3 are equivalent properties. If one is true, the others are automatic. And it is for the third one, we say a continuous linear transformation, we also call it a bounded linear transformation. It is the same word, I will use sometimes this, sometimes that, I mean one and the same thing, because continuous linear transformation takes bounded sets to bounded sets, and if a linear transformation takes bounded sets to bounded sets, it is automatically continuous. Okay. And then if T is a continuous linear transformation, then you have the following are all equal. Sup of norm x less than or equal to 1 norm of Tx equals sup norm x equal to 1 norm of Tx, sup x not equal to 0 norm of Tx by norm x. All these numbers are equal, you can prove this. Okay. and I am going to call this common number, so definition, as norm of t. So, a linear transformation is continuous, it is enough to check at the origin or check anywhere you like, or check if it takes bounded sets. And in such a case, these three numbers are all finite and equal, and I am going to call that norm of t. Then you take set of all continuous linear transformations from E to F, that is again a vector space, because I can define addition T1 plus T2 of x is T1x plus T2x, alpha t of x is alpha times t of x. So, I can define like this, and this becomes a vector space, and this is a norm on that vector space. Okay, so, that is also a norm linear space. So, norm T defines a norm on L of EF. So, norm, so you take two norm linear spaces, take all continuous linear transformations between them, that itself is now a norm linear space. And the fundamental inequality is you always have this. Norm of Tx is less than norm T norm x, and norm of the identity map is always 1. So, we said if E is a norm linear space, then if I define d of x y equals norm of x minus y, it becomes a metric space, and then you know what is a complete metric space. Every Cauchy sequence must converge. So, if ED is a complete metric space, we say E is a Banach space. Now, if I take F equal to the scalar field, real numbers, then I look at L of EF, ER, namely all continuous linear functionals. Now, this is called E prime or E star, and this is called the dual space. So, space of all continuous linear functionals. Functionals, we say whenever it is a scalar valued function. This is called the dual space, and whatever E is, E prime is always complete. Okay. So, whatever E may be, E dash is always complete. No, E any non-linear space, E dash is always Banach. Okay? Because when you have LEF, if F is complete, then LEF is complete. We do not care about E. We are really, when you look at linear transformations, the domain range space is what matters. So, if F is complete, then LEF is complete, you can prove that, and because R is always complete, you know that. Okay. So, LER is always complete. So, the dual space is always a complete space. Okay. So, this is more or less all that I am going to assume. Okay. So, if you are still uncomfortable, do not worry about all this. Think of, whenever I say E, think of Rn. Whenever I say F, think of Rm. Then every linear transformation is automatically continuous, and so you do not have to worry about whatever I say. Just these inequalities you remember, and that is it. Because whatever I am going to say now, it does not matter whether it is finite dimension, infinite dimension. Okay. So, at no extra cost, I can give you a more general theory, and hopefully if some of you like it, it is fine. If you do not like it, just think of E as Rn, F as Rm, and you are done, your multivariate calculus will still be there. Okay. But this way we are able to define the derivative of a function which is from a non-linear space taking values in another non-linear space. So, from we are going very far away from R to R. Okay. So, let me go back to F from R to R. And what is the derivative at A? So, f of A plus H minus f of A minus f dash A at H equals little o of mod H. This is what we wrote some time back, and this is what I am going to try to generalize now. So, there exists f dash A real number such that now I won't look at f dash A as a real number. I will look at f dash A as a linear mapping of R into itself. So, given any real number A, I can think of A as a linear transformation of R to R. How? A acting on any x is nothing but multiplication of A and x. This is a linear transformation. A of x plus y is A x plus A y, A of alpha x is alpha, A of A times alpha x which is alpha times A x, etc. And I told you in finite dimension every transformation is continuous. So, I am now thinking of A. So, now f dash A is no longer, I am looking at it as a real number, but as a linear transformation of R into itself such that f of A plus H minus f of A minus f dash A acting on H is little o of H. Okay. Is this way of looking at it okay with you? I have not done anything, I am just talking some different language, that is all. Otherwise, the equation is still the same. F dash A bracket H is nothing but f dash A into H. Okay. So, now I am going to look at, so we will write a definition. Let E be a nonlinear space, E F be nonlinear spaces. Let U be an open set let F be a mapping from U to F. So, I have a nonlinear space, I have an open set there. From that open set, I have a function which takes values in some other nonlinear space. let A belong to U. We say that f is differentiable at A if there exists a T belonging to L of EF. That means, if there exists a continuous linear transformation from E to F such that f of A plus h minus f of A minus T times h is little o of norm h. So, you see I am just copying. So, this last part only change I have made is f dash A into h I am writing as T times h. T is a linear transformation, h is a vector, so it acts on. So, if there exists such a transformation, then I say f is differentiable at E, and we write f dash A equal to T. Yeah, very good question. In next 5 minutes we will answer that. Yeah. Okay, is the definition acceptable? So now by a derivative I mean a bounded linear transformation from first space into the second space, and that obviously depends on the point at which you are taking the derivative, and that is where I give this notation f dash. So, first remark, if f is differentiable at A, then it is continuous at A. So, you know this in one dimension. If you have a real function which is differentiable, then it is definitely a continuous function at that point. Differentiability, continuity, all these are local properties. So, you have to say differentiable at A, differentiable continuous at A. When I say differentiable or continuous, then I am talking of something over all points, which I will come to later. So, why is this so? Suppose it is differentiable, then I know that f of A plus h minus f of A minus f dash A times h equals some epsilon h, where epsilon h by norm h goes to 0 as norm h goes to 0. Then I will write norm of f of A plus h minus f of A equals norm of f dash A h plus epsilon h. I am just taking one term to the other side. Now, apply triangle inequality, you have sum of two quantities. So, this is less than norm f dash A h plus norm epsilon h. And I told you a fundamental inequality about bounded linear transformations is that this can be plus norm f dash A times norm h plus norm of epsilon h. Now, let h go to 0, this term will go to 0, because when h goes to 0, norm h will go to 0. So, this first term will go to 0. What about the second term? Even if you divide it by norm h, it will still go to 0. So, it will epsilon h will automatically go to 0.
So how are we justifying norm of f dash of A is bounded because it's a bounded
Yeah, that is very definition, no, I am saying it is a bounded linear transformation, only then I will talk about it. So, I can write norm f dash. So, this goes to 0. So, as h goes to 0, this difference goes to 0. So, that means it is a continuous function at A. Okay. Now, second remark, this is related to the question he asked a few minutes ago. Now, this definition I have not been totally honest. Okay. I said if there exists a T such that this happens, and I happily gave you this notation also. But what guarantee is there? There is only one bounded linear transformation which will do this. There may be more. So, the derivative has to be unique. Okay. So, if it exists, so remark 2, if it exists, derivative is unique. And that is where the open set comes into play. That is why I work with open sets. I can work of course with the whole space, but it is enough if I work with open sets. Why? So assume there are two of them. So, f of a plus h minus f of a minus T1 h is say epsilon 1 of h, and f of a plus h minus f of a minus T2 of h equals epsilon 2 of h, where so epsilon 1 of h by norm h and epsilon 2 of h by norm h go to 0 as norm h goes to 0. Suppose we have two bounded linear transformations. Subtract, then what do you get? T1h minus T2h equals epsilon 2h minus epsilon 1h. So, norm T1h minus T2h equals less than or equal to norm of epsilon 1h plus norm 2h by the triangle. Now, you take x naught, any unit vector, and look at h equals t of x naught. Then what will you get? You will get mod t times norm of T1 x naught minus T2 x naught is less than or equal to epsilon 1 of T x naught plus epsilon 2 of T x naught. Now, divide by mod T. Now, what should I do? I should let t go to 0. If t goes to 0, this will go to 0, this will also go to 0. That means T1 of x naught, this is independent of t, it is less than something which goes to 0, and therefore, norm of T1 x naught minus T2 x naught equal to 0. That is T1 x naught equals T2 x naught for all norm x naught equal to 1. And then obviously, it means that T1 of x equal to T2 x for all x.
Why we cannot do that in without taking x naught,
Ah.
we cannot do that in that step itself. If the normal edge tends to 0.
Yeah, no, because I want something to go to 0, right?
Yeah, if I divide by normal edge,
Yeah. I don't want something to move. I want something fixed on this side. Okay, that's why I made the norm go to 0 rather than. So why is this an open set? Because if U is an open set and A is a point inside it, then I can have a ball around A which is contained inside U. So for every x naught such that norm of x naught equal to 1, I have A plus T of x naught belongs to this set for T sufficiently small. Okay. Now if U were not an open set, say suppose it included the boundary also, then I will have a neighborhood like this, then all x naughts cannot be included, only some x naughts, some directions are allowed. Because I am inside fully, all x naughts I can take. If I am somewhere in the boundary, I can only take some directions. Okay. So that is why, but I need to show that T1 equals T2, I need to show that for all directions it agrees. So I need open sets. Okay. So the uniqueness of the derivative, which is fundamental, is possible only when you take, like if you define the derivative in the interior, you are fine. The moment you come to the end points of the interval, you have trouble, right? You have only one sided derivative. Why? Because a neighborhood, the left side or the right side is excluded. So you cannot talk about proper derivative inside. Same reason, if you are in higher dimension, you need a whole ball inside, and that is possible only if you are in a open set. Okay, so this is the definition of the derivative. So now I will right away define for you directional derivative. This means derivative in one direction only. So this is the limit. So let x naught be fixed. Then the directional derivative of f at A in the direction of x naught. So when you talk of directional derivative, there is a function, there is a point at which you are taking this derivative, and there is a direction in which you are taking that derivative. This is nothing but limit as t goes to 0, f of A plus t x naught means f of A by t, like in one dimension, because you are worrying only in one direction. Okay. So I am taking increments only in one direction. So then I call it directional derivative. So if, so remark, f is differentiable at A, then the directional derivative at A exists for all directions and in the direction of x naught it is equal to f dash A evaluated at x naught. F dash A is a linear transformation. I can evaluate it at x naught. Why? Because if we take f of A plus t x naught minus f of A minus f dash A evaluated at t x naught, this is little o of t x naught. Okay. So, divide throughout by t. Here t comes out because it is a linear transformation, and then I divide, nothing is left, this divided by t. Now, let t go to 0, this should go to directional derivative, this is as it is fixed, and this goes to 0. So, this limit is equal to this. So, directional derivative is nothing but the derivative evaluated at particular direction. So, now one should ask the question, if the directional derivative exists in all directions, is the function differentiable? Okay. So, I said if the function is differentiable, the directional derivative exists in all directions, and it is, I gave you how to calculate it. Now, converse, suppose the directional derivative exists in all possible directions, is the function differentiable, and if so, what is the derivative? Unfortunately, the answer is no. The directional derivative can exist in all directions, but still the function can fail to be differentiable. This again because this first thing which I said this morning, limits along one direction or some directions may not be the same as limit in along all paths. Okay. So, we will see an example in the tutorial this afternoon. So, converse not true. So, f can have a directional derivative at A in all directions and yet f can fail to be differentiable. So, f is a function from u contained in E going to f. So, E and f are non-linear spaces, u contained in E is an open set. So, this is the setup in which we are working. So, you if you would like, you think of E and f as Rn and Rm. So, suppose f dash of A exists, assume, at all points of U. So, continuity at a point. Then when you say f is continuous, it means continuous at all points. So, same way differentiable at a point, differentiable at all points, then you say differentiable. Okay. Then we say f is differentiable on U. Then I can look at this map, A going to f dash A. Where is this map going? So, this map is A belongs to U, which is contained in E, and this is going to f dash A, which belongs to L of E f, which is also a normed linear space. This is a new normed linear space. Okay. So, I have a normed linear space E and another normed linear space L of E of f, and I have a mapping which takes A to f dash A. You can ask me, is this map continuous? Okay. If this map is continuous, then we say f is continuously differentiable. Okay. So, if this map is continuous, we say f is continuously differentiable on U.
If is defined on U only, sir,
Mm.
then how f dash of how f dash become L of E comma U?
No, no, f dash A for any A in U, this is a member of LEF, that is how we have defined it. That is how the definition we have given. F dash of A, the derivative is now a continuous linear mapping from E to F. That is the definition. It is a continuous linear transformation from E to F. Okay. That is how it is defined. So, f dash of A is always in L of E of F, that is where it lives. That's okay. Now, we have to do some examples, we have not. So, let us take example. So, EF normed linear spaces, and let us say C belongs to LEF. C is a bounded linear or continuous linear transformation from E to F. Now, I am going to define Fx equals Cx plus D, where D is in E. Affine linear map. What is this differentiable? What is its derivative? What is the derivative of a linear function in one dimension? Derivative of a linear function is a constant. Okay. So, here also I must get something like that, but I told you derivative is a bounded linear transformation. So, what do I mean by saying derivative is a constant? Okay. We will see in a moment. So, let us try to how to compute the derivative. We have to take increments and see. So, what is f of x plus h minus f of x? This is C of x plus h plus d minus C of x plus d. So, C of x will cancel, D and D will cancel. So, you are just left with CH. H is a vector now, remember. Huh? D belongs to F. Thank you. Thank you. Thank you. Thank you. Of course. D must belong to F. So, f of x plus h minus f of x minus ch is in fact 0. So, it is much more than what I hoped for. What did I want? I want something little o of something, but I get just 0. So, I am very happy. So, I can write f is differentiable at all points x and f dashed x equals c. So, this is what I mean by saying derivative is a constant. It is a constant bounded linear, it does not depend, the bounded linear operator does not depend on the point where you are differentiating, it is always the same bounded linear operator. So, derivative of a bounded linear transformation of a linear affine linear map is just a constant bounded linear transformation independent of the constant means independent of the point at which you are differentiating. So, it is always this. Let us do one more example. Let us take V E equals F equals say Rn. And let me take A be a symmetric n by n matrix. And B is also in R. So, x for me is x1 xn. Actually, I will want it as a column vector xn. So, x transpose will be x1. Okay. And I am going to define f of x as 1/2 x transpose Ax minus B transpose X. Okay. So, if you want it in terms of coordinates, this is 1/2 of sigma ij equal to 1 to n Aij xi xj minus sigma I equals 1 to n Bi xi, quadratic form. So, let us try to compute its derivative. So, you would have done it in partial derivatives, you would have, you know how to do, but then let us see what the total derivative looks like. So, f of x plus h minus f of x. So, h is in Rn. So, this is 1/2 of x plus h transpose Ax plus h minus B transpose x plus h minus 1/2 of x transpose Ax minus B transpose x. So, if you expand this, you will get 4 terms. You will get x transpose Ax, that will cancel with this. Then you will get 1/2 of X transpose AH plus 1 transpose 1 half of H transpose AX plus 1 half of H transpose AH. Then here you have two terms minus B transpose X, and this will get cancelled, and so you have minus B transpose H. Okay, I have just done expanded matrix multiplication. Is this all right? So now look at this. So f of x plus h minus f of x minus, now these two terms, so x transpose AH and then you have H transpose AX, but I can, because A is a symmetric matrix, so this is equal to X transpose A transpose H, because it is a scalar, it is its own transpose. But then A transpose is the same as A, because A is a symmetric matrix, so it is same as this. So 1 half plus 1 half, this can be written as agreed? Okay. So now I will write this as X transpose AH minus B transpose H equal to 1 half of H transpose AH. So now look at H transpose AH. I will get a norm H from here. Norm of AH is less than norm A into norm H. So, I will get norm A into norm H square. So, if I divide it by norm H, and this goes to 0 as norm H goes to 0. Okay. Agreed? So, this term is like H square. So, if you divide by H, it goes to 0. So, this whole thing is little o of norm H, because when I divide by norm H, it went to 0. Then my definition tells me this has to be the derivative. So, this quadratic equation function is differentiable at every point, and what is f dash of x? It is acting on any vector h is x transpose AH minus B transpose of H. And this is a linear operation on H. Let us do one more. Okay. Let us take all n cross n matrices. This is also a non-linear space. Okay. You can identify it with R n square if you like. So, given any matrix A, I am going to define f of A as A square. So, I want to ask what is its derivative. So, if I in one dimension, if I asked you, you would say 2A, okay. But now it must be a linear mapping on the matrices, okay. So, let us look at this. So, f of A plus H expand this, you get A square plus AH plus HA plus H square. You have to be careful because matrix multiplication is not commutative, otherwise I would have written 2AH. Okay. So, what is f of A plus H minus f of A minus AH minus HA equal to H square, and this is norm of H square is less than or equal to norm of H whole square. So, if you divide by norm H, it will go to 0. So, this is little o of norm H, and therefore, this has to be the derivative. So, f dashed of A acting on any H is AH plus H. This generalizes from the one dimensional case. So, f dashed of A, so f of A equals A square, then f dashed of A is 2A is what you know. What does this mean as bounded linear transformation? F dashed of A acting on H is 2AH. That is what we said we are going to look at. Now, 2AH unfortunately breaks up as AH plus HA because real numbers are commutative, but matrices are not commutative. So, one has to be a little careful. Okay. So, this is the thing. So, these are some examples. So, we will do some more this afternoon. So, we will see. So.